Okay, so again, you were to go through these problems yourselves. I will assume you've got some kind of answer written down, and we are simply correcting. Okay, if you need more details or whatever, then you can come and see me, or I highly recommend listening to the video when I'm done. So I'm going to do the first 7 of those. I'm going to show you one more sample question, and then I'm going to give you some time to work and ask me questions. Tomorrow we're going to talk about how your weight fluctuates in an elevator. We'll move into frictional coefficient in the near future. Plan on a gravitational fields test approximately mid to end of next week.
Oh my God.
It's a whole 10 days away.
Why officially won't be here? I'll be here.
We'll see how it goes. Okay, so question number 1. A skydiver in the spread eagle position opens the parachute, just like this. Is the diver accelerated? Yes or no?
No.
How many people say yes? Hands up.
Then you have to use the second one you need.
How many people say no? Hands up. A couple. Why do you say no?
He like decelerates.
Oh.
But technically it's the same as itself.
Lucas says that he decelerates, or he or she, I guess, doesn't say.
If you decelerate, is it the same
If you
as
slow down, is that acceleration?
Yeah.
Yes.
You voted for no.
I know.
Why are you going
Because
against your
I
own
thought of it
beliefs?
after.
Slowing down is a type of acceleration. Which direction is the acceleration? Because it's a vector.
Oh, okay, thanks.
The velocity is down, but the acceleration is up. Oh, so when they're opposite signs, remember, what does that mean? Slowing down. When the velocity and the acceleration are opposite, it means it's going to slow down. Now, does the skydiver actually, from a person on Earth, does the actual skydiver go upwards in the air?
Yeah.
No. Why does it look like that when you see that in videos and movies and stuff?
He slows right down.
Because the camera person is
Going
also going down. If they pull their ripcords at exactly the same time, what will it look like? They'll just stay face, like, as long as it's exactly the same time, they'll be still face to face. They'll just slow down. Okay. So a weightlifter lifts a 115 kilogram barbell from the ground. I just did, didn't I? I did. I said that is the diver accelerated? Yes, by slowing down. Which direction? Up. And I drew a little diagram and talked about it. A weightlifter lifts a 115 kilogram barbell from the ground. How does the force exerted by the lifter compare with the weight of the barbell? Is it less, is it more, or is it equal? How many people say less? No one says less. How many people say more?
Yeah.
How many people say equal? How many people didn't raise their hand? Well, it's kind of a trick question because it's more to begin with. How come? Because you got to get it moving. You have to accelerate it, but once you get it moving, it only has to be equal. So this is at the start when you have to accelerate it, and then they're equal once you get it moving. How does the force exerted by the lifter on the barbell compare with the force exerted by the barbell on the lifter? What did Newton's third law say? Equal and opposite.
What's that word under equal?
Equal and opposite. Get it moving. Once you get it moving, it's equal. I'll pause there while you're getting some of that down. Suppose you put a wooden block against a wall and push horizontally to keep it from falling. Okay, just like this. Draw a diagram showing the forces on the block and the causes of those forces. Pay special attention to the normal force and the weight of the block. Are they in the same direction and are they equal? Okay, well, the easiest of all the forces to put on there would be the weight force, right? Which would be down. Hopefully everyone got that. Clearly, with the hand like that, that would mean that the applied force would be directed inwards, right? If there was no applied force, which way would the block move? Downward. Friction always opposes motion. So which way is the friction here? Upwards. And the length of that should be equivalent to what? The weight force, down, right? Is this block accelerating at all, or is it at rest with no acceleration?
It's holding it there.
He's holding it there. So that means that the forces must be balanced, so there must be some other left to right force, right? Like this one here. F net is the sum of all forces. So I need another label for this one. That is the normal force, Fn. The normal force is always perpendicular to the surface, regardless of whether the surface is flat horizontal, or at an angle, or vertical, right? So left and right, those forces should balance. Up and down, those forces should balance. Therefore, what is the net force? The net force should be 0, right? Is this making some sense?
Sure. No, it's not. That's it.
Number 4, explain why an aluminum ball and a steel ball of similar size and shape drop from the same weight reach the ground at the same time. Well, I can answer that very easily. Why? The acceleration for both is minus 9.8 meters per second squared. They are of similar size and shape. They are of similar density. Aluminum would be lighter, but for the most part, they will reach the ground at exactly the same time. Why? They have the same acceleration, minus 9.8. Find out what the acceleration due to gravity is? We're going to do that coming up this week. We're going to drop balls and time them and figure it out. Give some examples of falling objects for which air resistance cannot be ignored.
Balloon.
Sure, balloons, paper, coffee filters, parachutes, feathers, birds, I suppose, birds, things that are relatively light. Well, a penny, I suppose. Do pennies reach terminal velocity? If they reach terminal velocity, right, then you cannot ignore air resistance. So yes, after a while, pennies certainly do reach terminal velocity. Give examples of falling objects for which air resistance can be ignored.
Balls.
What kind?
Anytime.
Ladies and gentlemen, the comedy team of Date and Gage, bringing fine comedy to you for hours and hours.
I don't want the ball jokes anymore.
It wasn't a joke though.
I know, well, yeah, you're right. Basketballs, yeah, basically things that are heavy. Yes, things that are heavy. Anything that is aerodynamic. Things like bullets. Dynamic, I spelled it wrong.
It's like a table.
No, things that are aerodynamic, not like tables. Things like bullets, javelins,
Oh, that makes
arrows, you can ignore air resistance, right? I suppose, if it's reasonably smooth, right? Okay, now number 7. Let's talk about number 7. It is clearly the hardest one here. In fact, you know what? If you haven't done these, how about you look at number 7 right now while I go do my attendance, because I really want you to think about number 7. Let's have a look at number 7. I just think I need the actual question here, right? The value of G on the moon, Lucas, I'm beginning here. The value of G on the moon is 1/6 of its value on Earth. In fact, it's 1.6, right? If you take 9.8, divide by 6, so gravity on the moon is about 1.6 meters per second squared. Will a ball drop from the same height by an astronaut hit the ground with a smaller or larger speed than on Earth? So basically you've got Earth and you've got Moon. What will be the speed? Will it be more or less?
Less.
How many people said less? Hands up.
Oh.
How many people said more? Hands up. How many people didn't put their hand up?
It'll be more.
How can we prove it?
We have to go to the moon.
You'd think so, but we can do it right here in the comfort of our own home.
It's accelerating like slower, so.
Can we just set the distance to be a 1 meter height? Sure, as long as it's the same for both, right? And here the acceleration is minus 9.8, and here the acceleration is minus 1.6. Okay? Velocity equals distance over time. Do I know? I don't know the average velocity, do I?
Another time.
And I don't know the time. The only thing I know is distance. It's going to be one of those kind of questions. Now, I do know the initial velocity in both cases is 0, right? If the initial velocity is 0, do I know the final velocity? Not without the time. But I do know that the average velocity would be the final velocity divided by 2, would I not? Right? How come? Because the initial is 0. So I'm going to replace this. I'm going to go VF over 2 is equal to D over T. Right? And the VF is in fact equal to what? The change in velocity, right? So change in velocity over 2. And I know my displacement is 1. Okay? I know, I'm just proving it here, right? Delta V, what's the formula for delta V? A equals delta V over delta T. So delta V is equal to A times T. In this case here, that's going to be minus 9.8 times the time, right? Remember us doing these on Friday? I'm going to take that value right there, and I'm going to plug it in for delta V. Just watch and learn. Minus 9.8 T over 2 is equal to 1 over T. I now have created an equation that has only one variable. That variable being time. Cross multiply. Minus 9.8 T squared is equal to? No. 2. 1 times 2. Okay. T squared is equal to 2 over minus 9.8. And I now have a problem. What is my problem? No. What is the problem?
Small number.
You can't take the square root of a negative. Is it imperative, is it absolutely necessary question that this is a minus 9.8?
No.
It's just acceleration down, right? That's all it is. Okay? So let's just ignore the negative and let's just keep it in the back of our mind that it's down. I'll just change those to positives.
Can you just ignore stuff?
Well, when it suits you, yes. I ignore students sometimes when it suits me.
Let's ignore it all.
It suits you to ignore this. Yeah, I knew someone was going to say that as soon as I said, oh, I'm in trouble now. I get a time of 0.45 seconds.
Wow. But negatively.
No, because time must be positive. Time must be positive. Now, the question really was, what's the question here? Will it drop with a smaller or larger speed than Earth? Maybe I should do part B first. Which one will take more or less time to fall? Okay. That was just on Earth. Nate, does all of that logic also hold true on the moon?
No.
All of this. The only thing that's different on the moon is that minus 9.8, right? So do I need to rewrite all that? No. On the moon, T is going to be the square root of what?
1.8.
No. 2 over 1.6. Which gives you a time of 1.12 seconds. So on the moon it's that. On Earth it's that. Which one takes longer to fall? on the moon. And if you stop and you think about that, if the acceleration is less, well, duh, it's going to take longer. But which one's going to be going faster when it gets to the bottom? This one is going to accelerate less, but it's also going to take more time.
So it is one.
So will it balance out? How can we decide? How can we do that? Well, it's quite easy because here I've got the formula right here. I've got VF over 2 is equal to D over T, right? VF over 2 is equal to my displacement, which is 1 over my time of 0.45. So VF is simply 2 over 0.45, or that doesn't quite work out for me here.
No.
Let's do it another way. I didn't like that. Let's go with this one here. A equals delta V over delta T. Acceleration is 9.8. Change in velocity, my time is 0.45. Change in velocity is 4.41. So Nate, on the Earth, when you drop it, it's going to be going 4.41. On the Moon, acceleration is 1.6.
Better be smaller, and if it's not,
Delta V, time is bigger.
you can tell 1, 2.
What is it?
Obviously.
1.8.
Oh my gosh, small.
It's going much slower.
Ah, I was right.
Much, much slower.
We just use common sense.
We use common sense instead.
Over
Hey.
hard distance to level out.
30 kids.
Yes.
Or just return the velocity first.
Now see, there's the problem, is that on the Moon, no air resistance. On Earth, lots of air resistance. This implies no air resistance, right?
All people think it's
Hello. Just ending. Can you put it on hold and I'll pick it up in about 2 minutes? Okay, thanks. 60,000? Okay, thanks.
I'm telling you myself.
Okay. If I'm not mistaken, I said do questions 1 to 7, right?
No.
Okay, so here's what I want you to do. I've got a phone call waiting for me, okay? Example number...
Wait,
Use phone if your timer is up.
I did. It's much less. I got 1.8.
Timer say no phone.
so just say smaller and
I
louder.
got 4.41 on Earth, and I got 1.8 on the Moon.
Just ignore me because you don't have
No, I'm ignoring it because I don't want to talk about cell phone.
Well, because you use the phone.
Smaller.
What about me? So I had part
Smaller speed, right? Right here, 1.8. That's fine.
Yes.
Okay.
But you never asked my second question. Will the ball take more or less?
It's right here. 0.45. 1.12.
So on the Earth it'll be faster.
Much faster, yeah. Yeah. Okay.
I got the second part.
I would like you to, I'm going to go take this call. I would like you to, with a partner, give that a try. I'm going to give you the answer to that. Okay? I want to see some progress. Don't just sit back with your phone playing Angry Birds or whatever. Say, I'm not going to do that. I want an answer. I want an answer.
Not right. Birds.
Get busy.
ASP, everyone. I'm just kidding.
Suppose that a ball is dropped from a 70-meter height tower, 70 meters high. How far will it have fallen after 1 second, after 2 seconds, and during the 4th second? Okay, so after 1 second, how far will it have fallen? I am solving for D. Does the 70-meter height thing matter?
Yes.
No, it goes further than 70 meters.
Which means that it has hit the ground and stopped. Exactly. So
Says you're doing it all wrong.
really, the 70 meters is irrelevant, right?
Why did you put it there?
Occasionally you're going to have questions like this, right? If you're doing a real problem at home, you might take a measurement that you don't need. Okay? How far, what's the one thing that's not given that you do need?
Time. I mean, not time.
Acceleration.
I'm not so worried about how fast a ball drops in the tower.
You have got the time. Okay, so what can I get out of A after 1 second? I guess I could do this. I could do this. Minus 9.8 is equal to delta V over 1. So the change in velocity is minus 9.8. And I guess I also need to know that the initial velocity was 0, right? Is that the final velocity? Yes, it is, because the initial is 0, right? Right?
Yeah.
Okay, but we want to know how far. The formula that has how far in it, the one with the D in it, has what V in it? V bar.
Ah.
0 plus 9.8 over 2, I guess technically negative. Right? Whoa, meters. Meters per second, right? Lucas, are you writing this down or no?
No.
Okay. I just need to know whether I should get after you or not.
Where?
So if the average is minus 4.9, now I can go V bar equals D over T. 4.9 is equal to D. My time is only 1. How far has it fallen? 4.9 meters. That's actually not that hard of a question.
Come on.
It's not.
I know where to start though. What if you don't know where to start?
Well, that's why you got to do practice. There's one mark there, one mark there, one mark there.
The first one we did, right?
How would you do part B after 2 seconds? You would do exactly the same thing, except you'd have a 2 in there, right? You could probably do it in your head. VF is going to be put a 2 in there, minus 19.6, right? V bar is going to be 0 plus 19.6 divided by 2, or minus 9.8,
Holy moly.
right? And how far does it go? What do you know? Back to 19.6. How come?
That's the first one we've given my own.
How come? Does it go farther in the second? Here's where it is after 1 second.
Big dumb lost point.
Here's where it is after 1 second. Here's where it is after 2 seconds. Does it go? How far does it go in the first second?
Still accelerating.
4.9. How far did it go in the second?
0.9.
Whatever that difference is, right?
14.
14 point. You're right.
Yeah.
How come it goes farther in the second? It's
Accelerating.
going faster.
Yeah.
It's going faster. How far does it go during the 4th second? How far during the 4th second? What is the 4th second? 0, 1, 2, 3, 4. There's the first one. There's the second. There's the 3rd second. The 4th second is between 3 and 4.
So you should do 3 and 4.
So you need to do 3 and 4 and then do what?
On average.
No, not on the average. How far does it go during the 4th second? How far did it go in the second?
Find the difference.
19.6 minus 4.9, right? So you have to do exactly those steps for 3, exactly those steps for 4, and then do what, Chandler? Just subtract, right? That's how far it goes in that second. All right, I'm going to stop talking because I can tell that I'm not reaching some people. I'm gonna do tomorrow, we're gonna talk about weight changes in an elevator. So I'm gonna give you the last 25 minutes to work on understanding free fall theory by completing the questions on here. Okay, and then getting into the problems as well. Anything where a person's weight is changing in an elevator, like question number 1, you should ignore for the time being.
If we just run down this pretty close.
Yeah, that's exactly what I'm saying, Nick. If you would just stop talking, you would actually have heard me say that.
You said this other book, like, that other book that's like, you get heavy.